In this video tutorial, we will discuss calculations involving curved mirrors. In our last lesson, we learned how to use ray diagrams to predict the properties of an image created in a curved mirror. By drawing ray lines coming from the object towards the curved mirror and reflecting off of it, where those reflected ray lines intersect, where they converge, that is where our new image is going to appear. From there, we can use the acronym SALT to describe the image as compared to the original object. In this case, the image size is much smaller than the original object, while its attitude is inverted because they're pointed in opposite directions. Its location is between C and F, and it is a real type of image because it appears in an area where light rays can actually exist. So it's on the same side of the mirror as the original object. But drawing a ray diagram is not the only way to predict the properties of an image. We can also make predictions using calculations. Now, in your assignment, you'll notice that there are answers at the bottom of the page. So in this case, questions 1 and 3 have answers, but not questions 2 and 4. That's because questions 2 and 4 are going to be marked for your assignment. I did this so you can practice these questions and check your answers at the bottom to make sure you're doing them right before you try out and do the assignment questions. The same is true for the next. You'll notice this is true for the next 2 pages. Every other question has answers at the bottom because the assignment questions are the ones that don't have answers at the bottom. So please make sure you're trying out the practice questions ahead of time and checking your answers to make sure that you are on track, that you're doing the questions correctly before you attempt the actual assignment questions. And please come see me for extra help because many of these sign conventions can be confusing. So let's try a sample question to get you started. Alright, so these are the equations that we will be using. M stands for magnification, so it tells you the size of the image. As an example, if M, magnification equals 2, that tells you the image is 2 times bigger. So the magnification would be 2x. If M equals 0.5, then that tells me the image is half the size of the object. So we say 0.5x. So anytime the magnification is greater than 1, that means the image is bigger than the original object. If the magnification is less than 1, that tells you the image is smaller than the original object. Alright, so M greater than 1, larger. M smaller than 1, smaller. Now HI stands for the height of the image. That's why there's an I there. Where HO stands for the height of the object. That's why there's an O there. Similarly, DI is the distance of the image from the vertex, while DO is the distance of the object from the vertex. And if you recall, the vertex is the point where the principal axis comes in contact with the mirror surface. So DI would be measured from the vertex to the image, while DO is the distance of the object from the vertex. Now you'll notice the DI variable has a negative sign in front of it. You must keep it there. So if you measure the distance of the image to be, let's say, 3 centimeters, you would have to write down negative and then the 3 centimeters. Now if the image had been on the other side of the mirror, we can tell the reader that the image is on the opposite side of the mirror by saying the distance of the image is a negative value. Alright, so negative distances means it's on the opposite side of the mirror in the virtual world, but if the distance of the image is positive, that tells you that it is in the real world. The image is on the same side as the object. Alright, so positive distance of the image means it's a real image located in front of the mirror. Negative distance of the image means it's a virtual image located behind the mirror. So real world distances would be positive 3 centimeters, while a virtual world distance would be negative 3 centimeters. So a real world distance would be positive 3 centimeters, but because there's a negative symbol built into the equation, when you plug it in to solve, it would just be a negative 3. But if the image was in the virtual world with a negative distance, we would have to plug in negative 3 centimeters. But due to the negative symbol that's already built into the equation, negative becomes a positive 3 centimeters when you plug it into the equation. Now when it comes to height, we have similar sign conventions as well. A positive height of the image means that the image is upright. So if the image and the object are both pointed in the same direction, it's upright, and we tell the reader it's upright by giving it a positive height of the image value. On the other hand, if the image and the object are pointed in opposite directions, we say it's inverted, and we can tell the reader the value is inverted by giving it a negative image height. Alright, so to recap, positive image distance means it's a real image located in front of the mirror. Negative image distance means it's a virtual image located behind the mirror. Positive image height means it's an upright virtual image located behind the mirror. And negative image height means it's an inverted real image located in front of the mirror. The last variable we need to talk about is f, the distance of the focal point from the vertex. In a concave mirror, the reflective side is on the inside of the sphere, so the inside of the curve. Because the focal point is in front of the mirror, so it's in the real world where light rays can exist, the focal length is given a positive value. So if you measure 3 centimeters from the vertex to the focal point, you would just plug in a 3 over here, so it would be 1 over 3. But with a convex mirror, the reflective side is on the outer part of the sphere, so the outer part of the curve. That means the focal point is behind the mirror in the virtual world. So the focal point in a convex mirror is always going to be negative. This is going to be a negative distance to show that it's in the virtual world. So if you measure 3 centimeters from the vertex to the focal point, you would have to write -3 or -1/3 because it's behind the mirror in the virtual world for a convex mirror. Alright, now when we do the calculations, make sure you pay attention to whether it's a concave or a convex mirror, negative or positive focal length. Now in this first question, we're dealing with concave mirrors, so we're going to be dealing with a positive focal length. Now when you do these calculations, I recommend you follow the GRASS method, where G stands for given, so what information are you given? R stands for required, so what are you required to find? A stands for approach, so which equation are you going to use? S stands for solve, so, solve it. And the last S stands for sentence. So write down your concluding statement. Therefore, the magnification of the mirror is blah, blah, blah. Alright, so use the GRASS method in order to help you organize your information. Otherwise, it's very easy to mix and match the variables, and then it's very easy to get lost. Alright, so let's begin. What I like to do is I like to read the question, and as I read, write down the information under the given section of what I'm given. A mirror produces an upright image that is 5.50 times 10 to the power -4 meters high. Because it's describing how high the image is, we say height of the image. Because it's an upright image, we give it a positive sign. Then finally put in the value 5.50 times 10 to the power -4. Now this value is expressed in scientific notation. If you don't know how scientific notation works, I'll put a link to one of my lessons in the description section. But continuing on, it says the object is 2 times 10 to the power -6 meters high. So positive 2.00 times 10 to the power -6 meters. Now it's important to note that the height of the object is always going to be a positive value. That's because we always compare the image to the object. The object is the original. So even if my object was pointed down, I would still say it's got a positive height. In this case, the image over here would be a positive. It would be upright as well. Even though they're pointed down because they're pointed in the same direction, this image is considered to be upright. Meanwhile, this one, even though it's pointed up, because it's pointing in a different direction than my original object, it's considered to be inverted. Alright, so just please keep in mind the object is always going to have a positive height value because that is what the image is being compared to. Alright, it then goes to ask what is the magnification of this mirror? So that's what I'm trying to find. What am I required to find? The magnification. Next, I need to look at the approach. So which equation should I use? Well, there's only one equation with magnification in it, so we're going to use this side. But more specifically, just this part. We're not going to worry about this part because the question doesn't ask for distance, nor does it give you any distances. It only gives you heights. So I'm just going to write down m is equal to high over ho. I can now solve by plugging in the values into the equation. So height of the image, 5.50 10 to the power -4. Height of the object, 2.00 times 10 to the power -6. Divide these two numbers and we get positive 275. Put in my final statement. Therefore, the mirror magnification is 275. So in this case, this mirror magnifies the image by 275 times. So the image is 275 times larger than the object. Now in this question, the magnification was a positive 275. But in some questions, you might get a negative magnification. So what does a negative magnification mean? Well, it means one of these guys, either the height of the image or the height of the object, must be negative as well in order for this equation to be true. But as we saw, the height of the object can never be negative, it's always a positive value. So if this must be a positive value, but magnification has to be negative, that means HI in this case would be negative. So if you see a negative magnification, that just means the height of the image is negative as well. So in comparison to the original object, it's inverted, so facing opposite directions. Alright, so negative magnification just means that they are facing opposite directions, that the image is inverted as compared to the original object. A common mistake that students make is they think that a negative magnification means that the thing is smaller. But as we saw earlier, a magnification of 0.5 means it's smaller. There's no negative symbol here, and yet it still means smaller. So when m is less than 1, then it's a smaller magnification. I guess technically it should be smaller than 1 but greater than 0 in order to prevent it from being negative. So essentially, if magnification is between 0 and 1, so a positive decimal number, then the image is considered to be smaller. While if the magnification is greater than 1, then it is larger than the original object. Alright, so the negative symbol on a magnification has nothing to do with its size. The negative symbol just tells you that it's an inverted image. It's the actual numerical value that tells you whether or not it's going to be larger or smaller. Alright, so I'm going to let you try the rest of these concave mirror questions yourself. Just a reminder, please check your answers at the bottom. So for instance, the question we just did had a magnification of 275x, where the x just means it's 275 times bigger, which is exactly what we have here. Although maybe I should put in the x to show that it's 275 times bigger. In any case, try out the questions with answers and compare them to make sure you're on the right track. And the ones that don't have answers, of course, you will submit as your assignment. Now, let's try one more question, but this time involving a convex mirror problem. Question 12 seems to be interesting, so let's try that one out. Again, we're going to use the grasp method to help us organize our information. It starts off by saying a 2.80 centimeter diameter coin. Now, what does the word diameter mean? Well, if you recall, the diameter is the distance across a circle as you pass through the center. So in this case, it's referring to the height of the object, in this case the coin. So the height of the object is 2.80 centimeters. So just be aware, sometimes these questions are worded in a weird way. You just need to decipher what it means and relate it back to how to solve our question. Now the coin, the object, is then placed a distance of 25 centimeters away from a convex mirror. Now just like the height of the object, the distance of the object must always be a positive value as well. Because if you put the object behind the mirror, well, then there's no reflection. The object has to be in front of the mirror in the real world in order for an image to appear. Alright, so distance of the object, positive 25 centimeters. Now it goes on to say that the focal length is negative 12 centimeters. So remember, convex mirrors must always have a negative focal distance. Sometimes the question will include the negative symbol, and sometimes it won't. Hint, hint. It is your responsibility to remember that convex mirrors always have a negative focal length. In any case, the question asks, determine the image distance and the diameter of the image. So image distance, so distance of the image, and the diameter of the image. But as we saw, diameter is the same as saying height of the image because this is a circular coin. So let's start the approach. Which equation should I use? Let's start plugging in values that we do have in order to determine which equation we should use first. So I'm given the height of the object, distance of the object, and focal length. Height of the object, distance of the object, and the focal length. And of course, distance of the object appears in this equation as well. Meanwhile, they want me to solve for the distance of the image and the height of the image. So di and hi. So now that I have all this information in front of me, here's the game plan. I'm going to solve this equation first. And once I have di, I can then plug it into this equation and solve for hi. So 1 over f is equal to 1 over do plus 1 over di. Punch in those values. F is a negative 12. Do is a 25. Now I'm not great with fractions, so I'm going to convert them into decimals. I can then bring the 0.04 onto this side. So negative 0.083333 minus the 0.04 gives me negative 0.1233333. Now be aware I've only solved for 1 over image distance. I didn't solve for image distance itself. So I'm going to flip the numerator and the denominator on this side. But because it's an equal sign, I got to do the same on this side as well. And now I've got 1 over negative 0.123333 is equal to di over 1. And I get negative 8.11 centimeters. So try to keep usually 2 decimal places for your final answer. And don't round anything in between. Alright, so during the calculation, don't do your rounding. Only round your final answer. And if I compare to the bottom of the page, the answer for DI is negative 8.1. So we're on track. So now that I've solved for DI, and I was giving HO and DO, I can solve for HI using this equation. So don't worry about the magnification part. It's not asked for in the question. It's not given for in the question. So just concentrate on this half of the equation. So let's start plugging in the values we do have. So the height of the object is over here, 2.8 centimeters. So 2.8 centimeters. The distance of the object, 25 centimeters, 25 centimeters. And the distance of the image was a negative 8.11. So I'm going to plug that in here as a negative 8.11. But don't forget, there's a negative sign already built into the equation. So I need to put this negative sign inside this bracket over here. So there will be two negative symbols side by side. Negative and negative turns into a positive, and then I'm going to multiply out the 2.80 to bring it up top over here. And I've got the 25 centimeters still left behind in the denominator. Punching this into the calculator, I get 0.908 centimeters as the image height. Now the answer says 0.909 centimeters, so close enough. And now I can write out my final statement. So therefore the image distance is negative 8.11 centimeters, or if you want to, you can say 8.11 centimeters behind the mirror. So in this one, you'd have to put the negative symbol because you're not telling me if it's behind or in front of the mirror. But over here, there's no need to write the negative symbol because you're telling me it's behind the mirror. So if you wrote negative 8.11 centimeters behind the mirror, that's a double negative. That'd be saying it's in front of the mirror. So it's like saying I'm not stupid. By putting the two nots, that means I am stupid. In any case, if you're confused by what I just said, leave it as distance is negative 8.11 centimeters. But if you really want to be fancy, you can just say positive 8.11 centimeters behind the mirror, and the word behind tells me it's a negative value. Meanwhile, because it asked for the diameter of the image, it didn't ask for height. You might as well use the same wording anyway. Diameter in this case and height are the same thing, but we're going to say the diameter of the coin is 0.908 centimeters. Now, because this height value is a positive number, that tells me that the image of the coin is standing upright as well. It's not inverted. It is upright and facing the same direction as the original coin. Alright, so there you have it. Try out these other sample problems and compare them to the answers at the bottom before you start doing the assignment questions.